Acids and bases are substances that are commonly found in our everyday lives. For example, acids give fruits like oranges and lemons a sour taste. There are several definitions of acids and bases that are used in chemistry. Our first definition of acids and bases is from a chemist named Arrhenius. An Arrhenius acid is a substance that increases the concentration of hydrogen ions in solution when it is dissolved in water. An example of an Arrhenius acid is hydrogen chloride gas, which has the chemical formula HCl. When gaseous HCl dissolves in water, it forms hydrogen ions, H+, and chloride anions, Cl- in aqueous solution. Since dissolving HCl in water increases the concentration of hydrogen ions in solution, HCl is an Arrhenius acid. An aqueous solution of HCl is called hydrochloric acid. An Arrhenius base is a substance that increases the concentration of hydroxide ions when it's dissolved in water. The hydroxide ion has a formula OH-. An example of an Arrhenius base is sodium hydroxide, which is a white solid and has the chemical formula NaOH. When NaOH dissolves in water, it dissociates into Na+ and OH-. Since dissolving NaOH in water increases the concentration of hydroxide ions in solution, sodium hydroxide is an Arrhenius base. Our second definition of acids and bases is from two chemists, Bronsted and Lowry. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Before we look at examples of Bronsted-Lowry acids and bases, we need to understand what is really meant by the word proton. A neutral hydrogen atom has a proton in the nucleus, and an electron outside of the nucleus. We represent a neutral hydrogen atom with an H, and a single dot next to the H to represent the one valence electron. If we take this electron away from our neutral hydrogen atom, we are left with a proton. So, in acid-base chemistry, whenever we are talking about a proton, we are talking about the nucleus of a hydrogen atom. Since a proton has a positive charge and is the nucleus of a hydrogen atom, we symbolize a proton by writing H+. We can also refer to a proton as a hydrogen ion. While it is convenient to write H+, a proton interacts strongly with a source of electron density, such as a lone pair of electrons on a water molecule. If a water molecule picks up a proton, a hydronium ion is formed. A hydronium ion has the formula H3O+. Chemists use the notation of H+ and H3O+ interchangeably, even if it's more accurate to write H3O+. The Bronsted-Lowry definition for acids and bases can be used whenever a reaction involves the transfer of a proton from one substance to another. Let's look at the reaction between HCl and H2O to form the chloride anion Cl- and the hydronium ion H3O+. If we look closely at the reactants and products in the balanced equation, this reaction involves the transfer of a proton from HCl to H2O. A lone pair of electrons on the water molecule takes a proton from HCl to form the hydronium ion H3O+. The two electrons that used to be in the bond between H and Cl end up on the Cl to form the chloride anion Cl-. Remember that a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Since HCl donates a proton, HCl is a Bronsted-Lowry acid. Since water accepts a proton, water is a Bronsted-Lowry base. When HCl donates a proton, it turns into Cl-. When water accepts a proton, H2O turns into H3O+. Let's look at another example. In this acid-base reaction, ammonia reacts with water to form the ammonium ion and the hydroxide ion. A lone pair of electrons on the nitrogen in the ammonia molecule take a proton from a water molecule. Adding a proton to NH3 forms NH4+. The two electrons that used to be in the bond between oxygen and hydrogen end up on the oxygen, which forms the hydroxide ion OH-. Since water is donating a proton, in this reaction, water is a Bronsted-Lowry acid. Since ammonia is accepting a proton, ammonia is a Bronsted-Lowry base. The reverse reaction is also possible. NH4+ can react with OH- to form NH3 and H2O. If NH4+ donates a proton, it turns into NH3. Since NH4+ is donating a proton, ammonium ion is a Bronsted-Lowry acid. If OH- accepts a proton, it turns into H2O. Since OH- accepts the proton, the hydroxide ion is a Bronsted-Lowry base. Conjugate acid-base pairs differ by one proton. So, on the left, water donates a proton and acts as an acid. When water donates a proton, it turns into the hydroxide ion. On the right, the hydroxide ion can act as a base and accept a proton. If the hydroxide ion accepts a proton, it turns back into the water molecule. Since there's only one proton difference between H2O and OH-, water and the hydroxide ion are a conjugate acid-base pair. If we take off an H+ from H2O, we get OH-. If we add an H+ to OH-, we get H2O. Another conjugate acid-base pair would be the ammonium ion, NH4+, and ammonia, NH3. If we take off an H+ from NH4+, we get NH3. If we add an H+ to NH3, we get NH4+. So there's only one proton difference between the acid, NH4+, and its conjugate base, NH3. In the reaction between ammonia and water, water donates a proton and therefore acts as a Bronsted-Lowry acid. In the previous reaction, water accepted a proton and therefore acted as a Bronsted-Lowry base. An amphoteric substance can act as an acid or a base. Since water, as we just showed, can act as either an acid or a base, water is an example of an amphoteric substance. Sometimes the word amphiprotic is used in place of the word amphoteric. Our last definition of acids and bases comes from the chemist Lewis. A Lewis acid is an electron pair acceptor. We can remember this definition by realizing, hey, both acid and acceptor start with the letter A. Since a Lewis acid accepts a pair of electrons, a Lewis acid must be deficient, or poor, in electrons. So, something with a positive charge, like a proton, H+, or the iron 3+ cation, could be a Lewis acid. Boron trifluoride, BF3, can also be a Lewis acid, even though it doesn't have a positive charge. If we look at the dot structure for boron trifluoride, the boron in the center of the structure has only 6 electrons around it, instead of a complete octet, or 8 electrons. So boron is capable of accepting 2 more electrons to get a complete octet. Since it readily accepts a pair of electrons, it is able to function as a Lewis acid. In contrast, a Lewis base is relatively rich in electrons, and is an electron pair donor. We can remember this definition by taking the D in donor and flipping it horizontally to form a lowercase b, like the B in the word base. An example of a Lewis base is the cyanide anion, which has a lone pair of electrons on the carbon. The ammonia molecule has a lone pair of electrons on the nitrogen, and can also function as a Lewis base. Let's look at the reaction between the iron 3+ cation and 6 cyanide anions to form the ferrocyanide ion. The ferrocyanide ion is an example of a coordination complex and has an overall charge of 3-. Since opposite charges attract, the negatively charged electrons on a cyanide anion are attracted to the positively charged iron cation. Each cyanide ion donates a lone pair of electrons to the iron cation. Since cyanide is an electron pair donor, cyanide is the Lewis base. Since the iron cation is an electron pair acceptor, the iron cation is, well, you guessed it, it's a Lewis acid. Since there are no protons involved in this reaction, we can't use the Bronsted-Lowry definition for acids and bases. In this example, we can only use the Lewis definition. Finally, let's look at the reaction of boron trifluoride with ammonia. Ammonia has a lone pair of electrons that it can donate to the boron atom. So, a bond forms between nitrogen and boron. Since ammonia is an electron pair donor, it is the Lewis base. Since boron trifluoride is an electron pair acceptor, it's the Lewis acid. For the product, the formation of a bond between the nitrogen and the boron creates a formal charge of +1 on the nitrogen and a formal charge of -1 on the boron. Once again, since there are no protons involved in this reaction, only the Lewis definition of acids and bases applies here. Alright, as a quick recap. There are 3 definitions of acids and bases that are commonly used in chemistry. An Arrhenius acid is a substance that increases the concentration of hydrogen ions when dissolved in water. In comparison, an Arrhenius base increases the concentration of hydroxide ions when dissolved in water. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor.